This video is going to be the last video in the carboxylic acid derivative series. We're going to start by talking about the amidate ion. So if we think back to the structure of amides, there's actually two protons that could be removed. The amide proton has a lower pKa, so we're going to see that proton be taken off rather than our traditional alpha proton. So this amidate ion allows for a very interesting mechanism. The Hoffman rearrangement uses the amidate ion in a halogenation reaction to make a primary amine. You'll note the halogenation reaction, your final product does not have a halogen in it. So if we look at this long chain with a carbonyl and a nitrogen group, so we have an amide, chlorine plus a base will give us our primary amine. Notice here that our carbon that's of the amide has now been released as carbon dioxide. So let's go through this mechanism. As we said earlier, the amidate ion is going to be generated, so your sodium hydroxide here is going to pull off that first proton, making your amidate ion. Your amidate ion is then going to react with one of the halogens. We've seen this reaction before. Think of it just like it's added to a double bond. At this point, you should be seeing that we have a brominated amine group. Now that that bromine is on, or halogen is on the nitrogen, that makes that hydrogen a little easier to take off. So a base can come and take that hydrogen off as well. So here we have an N-haloamidate. So this is very similar to our amidate with our nitrogen having a halogen on it. So it's still a minus charge on the nitrogen. The next step has the halogen leaving, giving us a single bonded nitrogen. This nitrogen can then go and rearrange, give us our R group on the nitrogen with an intermediate with our carbonyl. If we hydrolyze that species, we'll get our carboxylic acid, which can then be removed as carbon dioxide, and we'll get our primary amine. Other mechanisms in textbooks show this mechanism as a coordinated mechanism where it's happening all in one step. And so I think this arrows make a little bit more sense. So remember, this mechanism is called concerted, where all the arrows are your same intermediate that you see at the top of the slide, your isocyanide ion, which can then be reduced to your primary amine. The last thing we're going to talk about are alkane nitriles. Now these are not really carboxylic acid derivatives, but the carbon's in the same oxidation state, and we're going to go over some similar reactions to what we did see with derivatives, so they do end up getting grouped in. For nomenclature, our ic acid is going to be replaced with nitrile. So here we still have our same rules. We have a 3-carbon chain with a nitrile group on it. Here we have our 4-carbon chain with our nitrile group on it. And remember, starting from the 1 position coming from the carbon involved in the nitrile group, that's going to be position 1. So this functional group, as a substituent, we were calling the cyano group. So if it ends with the nitrile group, we're going to be calling it a nitrile. Nitrile can also undergo hydrolysis, right? Hydrolysis, just like with several other carboxylic acid derivatives, is going to give you your carboxylic acid, and so it will, if it's a dinitrile, it will become a diacid. Let's go through the mechanism in acid. We'll start with protonating the nitrogen of our nitrile. You can see here from the resonance structure, we have a positive charge on our nitrogen. We can easily rewrite that to have a positive charge on our carbon. This creates even a poor nucleophile like water can come in to relieve the carbocation. This next step here is a proton transfer. You can have the proton transfer coming from the amine, but make sure before you proceed that you have something deprotonating the extra hydrogen off of our newly added water. From here, just like with the carboxylic acid, our next spot that's going to add a proton is going to be our nitrogen. Remember, nitrogen is going to be more basic than oxygen. Here, just resonance structures, right? And remember, the goal of this is to create a carboxylic acid. So our next step should involve adding another proton to our amine. this will eventually leave as a good leaving group, and with our hydrolysis from here, you should see that our last structure is an amide. Amide hydrolysis was covered in the last video, so the mechanism from here to your end product carboxylic acid should be pretty clear. Remember here, since it's acid, we do have our nitrogen group being having a positive charge because it's the only way we can keep our carboxylic acid protein. In base, mechanism's a little bit more straightforward. We'll actually see our hydroxide adding as a nucleophile, kicking electrons out onto the nitrogen. Nitrogen can then pick off a proton from water, acting as base. Again, we've made something very similar to an amide, where that acid proton is going to be very easily taken off by hydroxide. So we'll have a resonance structure that can eventually look exactly like an amide, missing a proton. This nitrogen will then pick off the proton from water, giving us our amide. From there, you can see that our hydroxide can again act as a nucleophile, will protonate the amine group, and we'll be left with a carboxylic acid again and our ammonium ion. Organometallic reagents with nitriles, these are only going to add once, so you're only going to get ketones. Mechanism should be pretty clear, straightforward relative to what we talked about in the last video. So if you have a Grignard reagent, it's going to replace 2 of the bonds of the nitrile with an oxygen, as well as the other remaining bond being where the Grignard reagent adds. Remember that that oxygen that's left in your ketone is coming from your water. Other reagents that we talked about before with carboxylic acid derivatives, lithium aluminum hydride, we're going to add hydrogens to both sides of the triple bond, giving you a primary amine. And the only difference here with our reactions is that while we have a nitrile group with a carbon and a nitrogen, we're going to lose that nitrogen functionality with dibol, and you will be getting an aldehyde. So remember, any derivative with dibol is going to give you an aldehyde as your product functional group. That's it for carboxylic acid derivatives.